So our speaker is not Mahdi, but actually Marco
Scigliuzzo.
Scigliuzzo, who will tell us about quantum collective motion and macroscopic mechanical oscillators.
Okay, hello everyone. So I want to apologize, Mahdi couldn't come today because he didn't get his visa. So I'm giving his talk on his behalf. And today I want to talk about our result on quantum collective motion of macroscopic mechanical oscillator. So we saw during the session there are many ways to control mechanical oscillator, but our choice of platform is superconducting circuit optomechanics. And I just want to remind you that effectively our optomechanical system is basically an LC oscillator where we are able to couple the mechanics by a modulation of the capacitance due to the fact that one of the electrode is mechanically compliant. And this platform has been extremely prolific in the last few decades. We saw ground state cooling, squeezing of motion, mechanical entanglement. But you can see that all these platforms have something in common, basically this dome shape top electrode. And this is maybe not the ideal shape because the mechanical mode shape produces a lot of losses. Sorry. It's also, the gap is not very reproducible, and if you want to have large mechanical frequency or many mechanical frequency, it's going to be extremely hard to achieve this. So we developed this new fabrication method where we planarize the top surface, effectively having a flat top geometry for our mechanical system. And if we realize our drums, this is what we get. So you see it's a superconducting aluminum drum that is roughly 100 or 150 micrometer in diameter that is mechanically compliant. Here is suspended. And then, as I mentioned, we can shunt this capacitor with an inductor and forming our LC resonator. And the lifetime of this system is extremely long. You can see here the relaxation time after exciting the mechanical motion of the first vibrational mode, effectively giving a lifetime of 40 million. And this, so this fabrication process compared to the dome shape electrode give a lot of advantages, as you see here. So now we have a reproducible way to make this mechanical resonator. We can think to scale up the system. As many experiments has been done with single optomechanical platform, there are indeed as many theoretical proposals for collective optomechanics. For example, studying long-range interaction, topological phase of noise, even multipartite entanglement. But this has been extremely hard to realize in systems that go beyond only two modes or so. So in our experiment, we want to demonstrate our ability to indeed enter the collective optomechanical physics. And our experiment effectively just moved from a single mechanical system coupled to a microwave mode to many resonator. And now you can write the Hamiltonian of the system in the presence of the Redeton pump, and you can see that your microwave mode coupled effectively to a collective mode, the sum over B. And then if you recast indeed this Hamiltonian in the collective basis, you can see that you gain effectively a square root of n interaction. And this mode is indeed the one where all the resonators are in phase, and just to help the intuition is effectively the one that is depicted here in the picture. So now you can imagine that if we go to the clean room and we fabricate this device, we are not going to have a perfectly resonant system because of fabrication imperfection. But of course, you can also think that if you increase your Redeton pump, you effectively increase your optomechanical damping rate. And there's going to be a regime where this frequency scattering due to fabrication imperfection is going to be similar to your line with due to the optomechanical damping. And this is indeed the regime that we want to investigate. And again, you can even think to go beyond that part where you pump even harder and effectively having that your optomechanical damping rate is much larger than your frequency scattering. And if we realize the system in the clean room, we indeed, you can see here where we fabricate 6 mechanical resonator, and instead of having a single microwave mode, we indeed is gonna use a microwave modes. So effectively, three important aspects of this system are very important. The first, that our mechanical frequency scattering is extremely low. So we have 0.1% mechanical frequency fluctuation on sample. The lifetime of each system of the resonator average above 10 million. Here you can see the decay time of this system is again on the same second scale. And finally, this symmetrically coupled resonator effectively have two microwave modes that indeed implement the Hamiltonian that we want to study. So now we can do optomechanical induced transparency measurement that effectively measure on top of our microwave mode all the mechanical frequency. And you see that as we increase the cooperativity, or effectively the pump power of the red tone, we can see that all the individual line widths start to grow, but then they interact, and then they even go beyond and going thinner and thinner. And we can fit all these data and effectively collect them in a single plot, where we are going to plot we are going to extract the line width of all mode as a function of intracavity photon number or equivalent to the cooperativity. And effectively, you can see that for relatively small cooperativity, all the mechanical modes behave as individually interacting with the microwave cavity. And the cavity is just as a constant line width is there. But then something striking happen. One mode increases optomechanical damping rate, and the other 5 collective mechanical mode indeed decrease their optomechanical damping rate, even if the cooperativity is going larger. And this is effectively the hallmark of collective behavior. And then we can go even farther, where indeed we can reach strong coupling between the microwave mode and the collective mechanical resonator. So, as I mentioned before, now imagine that you have a strong radio-tuned pump, you will enter the strong coupling between the collective mechanical mode and your microwave cavity. But then what we can do now, if on top of this radio-tuned pump, we also excite the collective mechanical mode, for example, in this case, the collective mode, what we can do is indeed after exciting it, quench the coupling between the system, effectively turning off the radio-tuned pump, and collect the spectrum, the quadrature of the spectrum. And then just by Fourier analysis, we can indeed reconstruct exactly the amplitude and phase of whatever mode we decide to drive there. And if we put this data like in a plot, you can see that both for the bright collective mode and for all the actual other mechanical dark mode, you can very well extract phase and amplitude of the mode shape, as well as reconstructing according to theory, and they match pretty well. And finally, of course, you want to be sure that you're able to cool down the collective mode to the ground state, and this effectively we can measure just by collecting the spectrum and fitting to theory. And you can see here that the collective bright mechanical mode goes beyond 1 as an occupation. And effectively we are limited by this capped heating. And these are very interesting state, because effectively is the collective mechanical mode that is cooled down to the ground state. But if you go and take a look, we don't have probe cavity, we cannot hear. But if you were to look at the temperature of the individual mechanical system, they will be indeed still thermally populated. So this already brings me to the conclusion of the talk. I show indeed that after being able to have extremely low disorder in this mechanical resonator, allowed to enter in this collective optomechanical physics that can be extremely interesting. And indeed, the first step was preparing a collective ground state. And we are working now towards achieving collective squeezing and also entanglement. But this platform has more rich physics. For example, you can think about multi-degenerate exceptional point, or in general non-Hermitian dynamics. So, of course, this is not only my work. Unfortunately, Mahdi, that is the first author of the paper, would have give it, but I want to thank all the elements of the group and also this funding agency. Thank you.
Thanks so much, and we'll go ahead with questions.
Thanks, Marco, for the nice results. I have a question about this collective cooling. So in this plot, you show that you go like below the like to the ground state already for like 10 to the 2 more or less cooperativity, but the collective like the collective mode you said starts to appear at 10 to the 4 more.
Yes, so this is not exactly so. I didn't put this in the slide for time constraint. Effectively, you can define a fidelity or how collective you are, and they did the maximum collective mode is of course where you have strong coupling, but even before in this particular sample, the problem was that the collective microwave mode was extremely low coupled with the waveguide. So as soon as its line is very small, so it's very, I mean, you enter the strong coupling very very fast, and is also very hard to pump. But in future implementation, we are able to bring, or not in future, in implementation that we already made, we are able to bring this system up to maybe around 500 cooperativity. And so, yeah, the collective cooling is effectively like almost 100% fidelity, the one that we cooled down to the ground state. But you're right, in the minimum of the ground state here is not 100% collective.
So